Hello everybody. So in today's video we're going to talk about two things. We're going to talk about the difference between a physical and a chemical change, and we're also going to talk about neutralization reactions. So if you want to take down your title, the first one we're going to have is just physical and chemical changes. You can pause the video and just press play then when you're ready to continue. So physical and chemical changes are things that we see a lot of the time in the world around us. Whenever you see something that seems to have changed appearance in some way, or to have changed its properties, it's either a physical or a chemical change. So the key difference here is that in a physical change, a new material has not been made. And in a chemical change, there's been some kind of a chemical reaction and a new material has been made as a result of that. This new material will be different from the material that was present before. If you're not sure if a physical change or a chemical change has taken place, a good thing to fall back on is the fact that physical changes are often reversible, so you can undo them, but a chemical change usually is very difficult to reverse, so it's a lot more difficult to be undone. You can pause the video now while you take down the properties of physical and chemical changes. When you're ready, you can press play again and we'll move on to the next slide. So here we have an activity that I'm going to get you to do. I want you to use the knowledge that you have now about physical and chemical changes to try and classify each of these changes here as being a physical or a chemical change. It'll probably take you a few minutes to do it. Try and slow down and make sure you're thinking about them. Has a new material actually been formed? If it has, then we call it a chemical change. If it hasn't, we call it a physical change. If you're not sure whether it's a physical or a chemical change, then a good fallback is to just think, is the change reversible? Can you undo it? And if you can, well, then there's a good chance it's a physical change. But if you cannot, then there's a good chance it's a chemical change. Although that's not always the case. It doesn't work 100% of the time, but it is kind of a good rule of thumb. So you'll see some examples of where it does and doesn't work here. Again, you can pause the video here, and once you are ready to get going and go through the answers, just press play again. Alright, so we'll go through the answers now. If we look at the first one, an ice cube melting. When the ice cube melts, it hasn't actually formed a new material. It was water before and it's still water now, just in a slightly different form. If we think about whether or not it's reversible, ice melting is definitely reversible because we can just freeze it again. So this will be a physical change. I'm just going to write the capital letter P or C, just so things don't get too messy here. For a kettle boiling, it's going to be very similar. It's still water. It was water before, now it's just water vapor. It hasn't actually formed some kind of a new substance. It's just changed its state. So changes of state are a classic example of physical change. You might think that it's very difficult to unboil a kettle, and you definitely might have a little bit more difficulty than refreezing an ice cube. But if you put the water vapor into contact with something cold, it actually will cool back down again and turn back to water. A good example from first year where we would have seen this is in distillation, when we boil a substance and then condense it back into water again afterwards. So this was a trickier one, but it is still a physical change. The next one we're looking at is gas burning in a Bunsen burner. So in this one, we did have gas, but it ends up being used up and a new material is made. When we burn something, it reacts with oxygen in the air, and it actually forms new materials. So when we burn a methane gas, it forms carbon dioxide and water vapor. So we have two new gases that have been formed in the air. Again, if you weren't sure about this one, well, you can just think, is it reversible? And really, it's not ever really possible to unburn something, as far as I'm aware. So this one will be a chemical change. Again, we know this because a new substance has been formed, the old substance is used up, and it's also irreversible. The next example of burning toast is kind of similar because it deals with burning something. So in this case, the bread actually has undergone a chemical reaction, and we get that kind of black stuff that forms in it, which is just a bit of carbon. And again, you can't unburn toast, although you can scrape the burnt toast off. So this would be a chemical reaction also. For dissolving salt in water, this example is something that can be undone because we could just evaporate the water off and get the salt back. We also know that when we dissolve salt in water, it doesn't form a whole new substance called salt water. It's just a mixture. Going back to when we covered mixtures, which can be separated out again relatively easily. So we'd say that this is a physical change. So the next one I think is a little bit tricky as well. Boiling an egg. So you might think, well, the substance was egg beforehand and it's egg afterwards. So I kind of understand that. So you may have put down that it's a physical change, but also just think here, is it something that can be reversed? And in this case, it's not. You can't unboil an egg. And actually, even though you might think it was egg beforehand and egg afterwards, the heat that the egg takes in when the egg is boiling causes permanent changes to the molecules that make up the structure of the egg. So this one we're putting down as chemical. Chopping a wooden log is next. This one you may have put down as physical, and that would be correct. We know it's a physical change because the chemical reaction hasn't happened. It's really just changed its appearance. So beforehand you had one big log, and now you've got two smaller logs. A new substance hasn't been made, it's just the same old piece of wood. It just appears slightly differently. Right, the next example also involves a wooden log. So this example is talking about burning a log in the fire. Burning is always an example of a chemical change. Again, a new substance is formed. When you burn stuff, it makes carbon dioxide and water vapor, so gases are released. You may also see a bit of ash for some of the stuff that didn't fully burn, and again, it's irreversible. You cannot unburn some wood. Okay, the next one is also a physical change. It should be fairly obvious that if you tape two sheets of paper together, a chemical reaction has not happened. And it's also very easy to reverse that change because you just take the piece of tape off and then you've gone back to your two sheets of paper instead of one big one. Okay, so I've saved two kind of tough ones for the end. Dissolving a tablet in water. This one here is a physical change. So you might think it's irreversible because you wouldn't be able to get the tablet back out necessarily. So I guess that's why I wanted to have it in there as a little bit of a trick. An example where the irreversible rule doesn't always work. But if you dissolve a tablet in water, you would still be able to get the material that makes up the tablet back out if you evaporate it off the water, although it wouldn't look like a tablet, so it would have undergone its own physical change then. Also, more than this, we know that if we dissolve a tablet in water, it isn't going to make a new substance. Instead, it's just going to be a mixture of the material in the tablet and the water. So making a solution or a mixture is just going to be a physical change. So the very last one, baking bread, I put in there. I'd say probably a lot of you guys put down chemical, and honestly, it is largely chemical for the same reasons as boiling an egg. That some reactions take place when you heat the materials you've mixed together to make the bread. But there are actually a few physical changes in there too. For example, some pockets of air inside in the bread will expand, and also some of the liquids that were inside in the bread will evaporate off, which is physical. So I guess maybe we can put down a bit of both for that one. Again, a little bit of a harder question there at the end to make you think. But if you put down just chemical, that's fine too. Okay, so the main thing really that we want to look for when we know that a chemical reaction is going to take place, or when we're trying to find out if one has taken place, is just seeing whether or not a new material has been formed. But here's some other helpful points that may give you off may give you a clue as to whether or not a chemical reaction has happened. So if a chemical change is taking place, some of these might happen. Bubbles or fizzing could happen. Could give off, this is supposed to say, a smell. So it could be a bad smell or a good smell. It may make a noise, so like a pop or a bang or something. It might give off flames or sparks. And the material could get warmer or colder without you obviously heating it up or cooling it down. So you might just mix two materials together and all of a sudden they start giving off a lot of heat, for example, or all of a sudden they feel very cold to the touch. So I just want to touch here on something you probably would have done in first year and tie it back into our physical and chemical changes. And that's the law of conservation of mass. So the law of conservation of mass says the total mass before and after a chemical reaction will be the same. But this is also true for physical reactions. If I was asked to define it, I just mentioned the top line. Although according to the new curriculum, you shouldn't be asked to define it. So it's just also useful, I think, to know that that'll be true for physical reactions as well. So looking at an example of a physical reaction here, if we have an ice cube and we melt it, there's some fire underneath. If the ice cube weighed 8 kilograms before, then we would have a pool of water that has a mass of 8 kilograms afterwards. So the mass is the same before and afterwards. None of the material should disappear or no new material should come out of anywhere. And the same can be said for a chemical reaction. If we have a log of wood, and that log of wood weighs, for example, 1 kilogram, and we burn the log of wood, it's going to give off gases. So I'm going to draw that as a cloud here. It's going to give off carbon dioxide and it's going to give off water vapor. But those gases should also have the same mass as the log did, and that'll be 1 kilogram also. If you want to take down the definition for the law of conservation of mass, you can. It might just be useful to jog your memory when you're looking back at it again. Okay, so for the second half of this video, we're going to look at neutralization reactions. So this heavily ties into acids and bases and the stuff we've been doing for that already. I take down another heading here for neutralization reactions. The reason why we're tying them in with physical and chemical changes is because neutralization reactions are a type of chemical reaction. So I guess I just want to tie it back to that part of the course so that you're able to give an example of a chemical reaction just straight off the top of your head if you're ever asked. So what neutralization reactions are, at their most basic level, it's a reaction when you add an acid and a base together in the right quantities. They should neutralize each other. So their pHs will cancel out and they end up neutral. This means if we were to add a universal indicator after the neutralization reaction, it would show up green. So it's important to know that when we carry out a neutralization reaction, we're adding an acid and a base together. PowerPoint has shown up slightly different than it should have here. This should be an arrow. I'll draw it over there in a red color to maybe make it stand out from the box. But the arrow represents a chemical reaction, so it's a one-way street. This chemical reaction is irreversible, so it's not going back, right? So an acid and a base mix together and they form a salt and water. Now, when we hear the word salt, we often just think of table salt, the stuff we like to put on our food, and it makes everything taste better. You actually can make table salt by mixing an acid and a base together, but it doesn't always have to be table salt. There's different types of salt that can be formed, so we'll look at what they are in a minute. For now, it's just important to take down that an acid and a base will react together to give you a salt and water, and that's the key to our neutralization reaction. Can pause the video while you're taking that down, and then again once you're ready to resume, just press play. Okay, so here we've got two examples of word equations where we talk in words about the acid and base mixing together and giving us our salt and our water. I've fairly clumsily drawn some arrows across those boxes because they didn't come into the app again properly. So we follow the same structure each time when we're doing it. We have the acid, we have the base, we have the salt, we have the water. So I'd encourage you guys to just do it out in the same fashion as well when you're writing out any word equations you're doing. Now, word equations aren't specifically mentioned on the syllabus, so if you're finding this part a little bit hard, that's okay, but I just thought it might be something extra I could go through with you guys to give you a little bit more of an in-depth understanding of the topic. So what I really want you to, I guess, get your head around, and what I want you to take away from this is the salt that is formed is made up of the different elements in the acid and the base. So I'll talk to you a little bit about that now. So in the first example, we mix together hydrochloric acid and sodium hydroxide. Water is going to be formed, but the salt that is formed is sodium chloride. Now, the fact that we're getting sodium chloride, it contains the elements sodium and chlorine. Well, the sodium and the chlorine have to come from somewhere. So the sodium part of the name, it comes from sodium hydroxide, our base, and the chlorine part of our salt comes from the acid. So I've color-coded them there so you can see where they're coming from. Again, the first part comes from the base and the second part comes from the acid. If you look at the next one, you might be able to see that the same pattern is followed. So we have potassium nitrate. The first part comes from the base and the second part, nitrogen, comes from the acid. I've mentioned before that we could actually make table salt using an acid and a base. So sodium chloride actually is table salt, and potassium nitrate, however, is not. Alright, it just has a similar structure to table salt, and it falls into a category of chemicals called salts. Right now, I'd like if you guys could take down both of these examples and make sure to include your arrows going in the correct direction. And especially the first one, I think, is a good idea to pay attention to because it is the most common one that comes up in textbooks and questions in general. So here we've got a few examples of the acids and bases being mixed together, and my job for you now is to copy out both of these boxes and just match the acid and base up to the salt that's formed on the other side. So each of these has water, but the salt will be different. Again, you can pause the video now and just press play whenever you're ready to resume. Okay, so here's the correct answers done 8. The first one you can see, like before, we have hydrochloric acid and sodium hydroxide gives us sodium chloride as the salt. Sodium chloride. The other ones as well have sodium hydroxide as the base. So we end up with sodium being the first part of all the salts here. So the second one, we have nitric acid. Match that up to here, and we end up with sodium nitrate. And the final one that uses sulfuric acid, we're going to end up with sodium sulfate. Now again, knowing the names of the different salts isn't something that's specifically mentioned on the curriculum, so don't feel obliged to learn off all the different names. But I would just like for you guys to have a surface level understanding of how the names for the salts are come up with. If I was to give you an acid and a base and a similar question to this, you might be able to match them up, and I'd be happy enough with that. So one thing it does mention specifically in the syllabus is that you have to be able to investigate the reaction between acids and bases. So we actually know quite a lot about this type of reaction at this point. We know it's called the neutralization reaction. But if you're ever asked to show an experiment to investigate the reaction between acids and bases, this is what you would talk about. It's a process called titration. So for this titration reaction, we have a piece of equipment called a retort stand that has a clamp attached to it. The clamp is holding up a glass tube that's called a burette. Down below we have a conical flask that's filled with sodium hydroxide, which is our base, and it's also filled with methyl orange, which is our indicator. So we just have a few drops of methyl orange, that's all we need. Then we have our hydrochloric acid up the top that's being held inside the burette. The whole purpose of the burette is that it's able to release drops of the liquid inside it really, really slowly, drop by drop. And there's a little device here called a stopcock, and that controls the flow of liquid, so you can use that to speed it up or slow it down to just a few drops at a time. So once we have all of this equipment set up, we should notice that the methyl orange has turned our base orange. So again, it's an indicator, and this particular indicator turns orange when it's added to a base. Now we can adjust the stopcock to slowly allow the hydrochloric acid to trickle down drop by drop into our conical flask. As the hydrochloric acid is trickling down into the conical flask, we're going to be slowly swirling this flask. Slowly swirling it and looking for a colour change. The reason why we expect to see a colour change is that methyl orange is only orange when it's added to a base. So once this is neutralized, it will no longer be a base and it'll turn acidic, and we should expect to see a colour change then at that point. And that's when we'd close the stopcock. So the colour change we'd actually expect to see here is the methyl orange would turn from orange to pink once this is turned from basic to acidic. Now we'll know that it's been neutralized because we're going to stop it at exactly the point that it turns from being a base to being an acid. So before it has a chance to become too acidic from the addition of extra hydrochloric acid. Now there's a few little notes here about how to make sure this experiment goes as accurately as possible. So one of them is that you want to make sure there's a white substance underneath the conical flask. So you can add in a sheet of white paper underneath so you can see the colour really, really clearly. Or you can put it on a white tile or something like that. Another thing to be careful of to make sure your experiment is as accurate as possible is when it's getting close to neutralizing, you might see like little jets of pink start to appear here. And you might stop the stopcock and just see if it stays pink, or it might go back to orange once all the acid you've added has kind of dispersed throughout the rest of the liquid. So once it turns pink and it stays pink, then you know it's done. It would be possible to do this with a universal indicator and you'd see the thing go green. So if you're really stuck and you can't remember the name methyl orange in an exam, you could put down universal indicator, but it's not generally done. And the reason for that is because you don't see as abrupt of a colour change. It's more of a gradual change across the spectrum of the universal indicator's colours. Alright, so the last thing I'm going to go through here on this video with you guys is just a little, I guess, challenge to think about. So bee stings are acidic and they have a pH of about 3. So one of these things written here on the right hand side is actually a home remedy that you can apply to a bee sting to try and make it a little bit less painful. So one of them is bicarbonate of soda, which has a pH of 9, it's a base. Black coffee, which is a pH of 5, it's mildly acidic. Lemon juice, which has a pH of 2. Or water, which has a pH of 7. So you can make up your mind now which one you think would be the best to add. And press play when you're ready for the answer. So hopefully you said that you would add bicarbonate of soda, because this is a base. So if you add the correct amount, it will neutralize your bee sting, which we said is acidic. I think the way that people do this is they make up a little paste of sodium bicarbonate and water and then just apply it over the bee sting after they've removed the sting. Obviously this is medical advice, so don't do it on my recommendation. I've actually never been stung by a bee, so I don't even know if it works particularly well. This is just a classic example that a lot of science teachers use. Okay, right, that's the end of this video. So just make sure that all your notes are taken down and they make sense. And if you have any questions, you can write them down into your copybook and then just send me a quick message on Schoology or an email or something like that, and I'll try and get back to you as quick as I can.